of having a rectangular plate, you have an axisymmetric or a cylindrical plate. So instead of having, so your plate would look something like this. All right. So we can follow the same process where we talk about the displacement along the radial direction. So in this case, I guess our axis is, our z-axis is here, our radial axis is here, and then our theta axis is going around z-axis. So we can talk about the strain within the radial direction, so displacement within the radial direction. Using that definition, we can say that the we can calculate the strain within the radial and the tangential directions. So, epsilon r and epsilon theta. And then just like we did in the rectilinear case, we can relate the internal stresses, sigma theta, and sigma r, and tau, I think tau r theta, to our external forces and moments. So we have m of theta, m of r, and maybe there's an m of theta somewhere. Maybe not. There might not be a mr theta in this case, but so again, we can relate our strains that we defined here, our epsilon r and our epsilon theta, to our sigma r and our sigma theta using our stress strain relationships for cylindrical coordinates. So we get now our stress and our strain, our stress in our radial direction, our stress in our tangential direction are going to be just a function of the displacement W and the elastic properties of our materials. So we can, using this figure here and doing a moment balance over the areas, we can relate m of r and m of theta to our applied stresses, sigma, our internal stresses, sigma r and sigma theta. And then if we substitute in our radial and our tangential stresses into these equations, we can solve for the moment and the moment in the radial direction and the moment in the tangential direction. And again, the d is just the flexural rigidity that we had the same for the rectilinear case. And then so again, because the one thing you'll notice is that unlike the rectilinear case where we took the derivative of w, the partial derivative of w with respect to both x and y, in the radial case we have everything is with respect to just r. So now we have, instead of having a partial differential equation, we have an ordinary differential equation. So we can solve it more directly. So now that we have equations for m of r and m of theta, we can solve for the stress within sigma r in the radial direction and the theta direction. And these will be the maximum and minimum stresses again will occur at plus or minus t over 2. All right. So and then the only thing that's left is we don't know what w is as a function of r. So we need w to calculate m of r and m of theta. So in order to calculate w of r, we can use the this ordinary differential equation that we have on the bottom here. So this equation here is an ordinary differential equation that we can solve directly. It will still depend on the boundary conditions of the problem. We'll change the solution, but you can solve this ordinary differential directly, and you can get a continuous solution. So you can solve for the w as a function of r, and you can solve for the moment as a function of r. So you can for both the tangential and the radial direction. So we can get, because we can do this, we can determine the displacement or the shape of the entire plate along the entire width, and we can determine the moment at any point. So since we can determine the moment at any point, we can determine the stress at any point. So we can use, so for circular plates, we can solve directly for the stress and the shear distribution, the stress distributions and the displacement distributions using this equation, and some of the solutions for common types of plate problems are shown in the following on the next page here. So, so depending on how that plate is supported and the loads that are being applied to the plate, it will have the following basically within each of the cases that are described. It'll give you W, it'll give you which is the displacement, it'll give you the slope as a function of the radius, and it'll give you the moment and the in the radial and the theta direction. Okay, so from the moment in the radial and the theta direction, you can determine the stress in the radial and the theta direction. Okay. And using those two stresses, you could then determine if the material will fail, will plate fail. Okay. So they have the different types of cases for the plates. The one thing I guess that's a little confusing about these tables is that when you look at them right away, it looks like a rectangular plate, but all of these are like really just looking at a side profile of a round plate. So just keep that in mind when you're looking at these. So there's a lot of different tables, right? And the one thing that I want to bring up for all plates, and this isn't just deal with rectangular plates, circular plates, is that if you can use the superposition principle just like you did with like with beams that you've been using the whole time. So like if you have two solutions or you have multiple loads that are being applied to the plate, we can like that basically don't fit like one of these conditions that like each of the loads individually fit the cases that are described in these tables. You can add the two solutions together to get the desired answer. So